Okay, well, I did it again. When I hit the button for record, I didn't hit it hard enough and it didn't record. So I've already written out the solution to this problem. Let's go through it again. Well, me for the second time, you for the first time. This is number 59 from chapter 6. This is part of your assigned homework, which you've already submitted. And that means that you can find a publisher solution on Canvas, but I will present to you a simpler method of solving this problem using proportional reasoning. We really just need that fact that drag is proportional to the square of your velocity, and that when you're going at terminal speed, your drag force equals your weight. Those two facts will allow us to solve this more simply than the method that your solutions manual used. So this problem has two parts, A and B. In the first part, you're supposed to imagine that a ball is shot from a compressed air gun. So here's my compressed air gun. This vector is the velocity showing that this ball has been launched upwards. And we're told that the ball is launched so fast that it's actually going twice its terminal speed. So first, just imagine if you had the ball and you dropped it and you let it fall and go faster and faster until it doesn't go any faster. That would be its terminal speed. This ball is shot from the compressed air gun at twice its terminal speed. That's a lot like a bullet from a normal gun, right? If you just took a bullet and dropped it from the top of a very tall building, you wouldn't expect it to reach a speed as great as the speed at which it leaves the gun. I mean, think about it. Would you rather stand at the bottom of a skyscraper and wait for some bullet to fall and hit you on the head? Or okay, I won't even finish that question. You see where I'm going with that. Okay, we're supposed to figure out what the acceleration of this ball is. And the first thing you might want to do is set up your coordinate system. I will go ahead and call up the positive direction. I will draw a dot to represent the ball. And now you want to recognize that since the ball is moving upwards, the drag force has to point downwards. That's different from the skydiver example where the skydiver was falling down and drag pushed up. You always assume that the drag force is opposite the velocity. Wouldn't it be strange indeed if drag made you go faster? If you were skydiving and suddenly you felt the air giving you a push that made you go faster, that's not going to happen. Okay, so I've drawn a drag force downwards and a gravity force downwards. And since they're both pointing in the same direction, you're going to get a net force that's also downwards that's even longer than gravity. So we would expect the acceleration to be even greater than free fall acceleration. Here's the quick way to solve this problem. If you remember that drag force is essentially more or less proportional to speed squared, that would imply that if you're going twice as fast as the terminal speed, the drag force would be 4 times what it is at terminal speed. So I'm using d sub t to mean the drag force at terminal speed. What I've written here means the drag force evaluated at this particular speed. Doubling your speed means quadrupling your drag force. So if you're going twice as fast as terminal speed, your drag force should be 4 times what it is at terminal speed. Excuse me, coronavirus. No, not really. What is the drag force at terminal speed? That's one of the basic facts that you just want to memorize. If you're going at terminal speed, the drag force is equal to your weight. That's why you're not speeding up. So in other words, the drag force will be 4 times the weight of the ball when it's going twice as fast as terminal speed. Now that I've got values for those forces, I can use F equals ma. So we'll take the net force along the y-axis, set it equal to mass times acceleration. Well, the drag force points down, so it gets a minus sign. Negative 4 times the weight, and then of course gravity is negative 1 times the weight. You'll notice that the m divides out from the equation. So it doesn't matter how massive this ball is, which is kind of interesting. -4, -1, we've got -5 g's. So it really didn't take much work to get to the answer. This thing will be slowing down at a rate 5 times as great as if there were no atmosphere. If you had fired this ball into the air and there were no air, Well, that doesn't make any sense. How can you fire it into the air if there's no air? You know what I mean? If you fired this upwards on a planet that had no atmosphere, it would slow down at a rate equal to g. If this was Earth with no atmosphere, it would be slowing down at 9.8 meters per second. It's actually slowing down much more quickly than that because gravity gets an assist from the air drag. And I think we could reach the same conclusion about a bullet, right? If you fired a real gun straight up into the air, that bullet's going to slow down a lot more quickly than just 9.8 meters per second. Why is it slowing down so quickly? Because there's significant air drag. Now, a bullet is purposely shaped to be aerodynamic. So it would presumably have less drag on it than a sphere of the same size. Part B is very much like part A, except for this time, the ball is shot downwards at twice its terminal speed. So that means the free body diagram changes. Because the ball is moving downwards, the drag force would have to oppose the velocity. The drag force is going to point upwards. And now, when you add these two vectors up, you're going to get a vector that's not as long as the net force was in part A. So since the net force is going to be smaller in magnitude, we would also expect the acceleration to be smaller in magnitude. And then you have to ask the question, since this is moving downwards, is it going to be speeding up or slowing down? Well, normally when you drop something, doesn't it start by speeding up? Gravity is going to make it go faster and faster until it stops accelerating at its terminal speed. Here, we've launched something that's already going faster than its terminal speed. And you can see as I've drawn it, the drag force is actually greater in magnitude than gravity. The net force will be upwards, which means the acceleration is upwards. And what's the rule? Anytime your acceleration is opposite your velocity, your object will slow down. So we actually do expect this thing to slow down. That's a little counterintuitive, that you could shoot something downwards and it would immediately slow down rather than speed up. Okay, when I plop in my forces this time, drag gets a plus sign because it points upwards. So we've got a positive 4 mg. That conclusion has not changed. The ball is still going twice its terminal speed, which says that the drag force would still be 4 times the weight. Minus a single mg is going to equal ma. Just like before, the masses divide from the equation. 4g is minus 1g, that's 3 g's is equal to the acceleration. Okay, so a markedly different acceleration in magnitude than part A. Now you may be thinking that because there's a plus sign, that would imply the ball's actually speeding up. But remember the rule, the velocity's down, the acceleration's up, hence the plus sign. So the ball is slowing down. And if you understand this problem, you could probably now answer that question that many of us have wondered. On various holidays throughout the year, some people like to shoot guns in the air in a display of joy and celebration. Other people don't care for that so much. I have a close friend who's next door neighbor. I think it's 4th of July. I forget which holiday, but she'll actually go into the closet, sit down, and put a cast iron pot over her head because she's afraid of bullets coming down through the roof of the house. Now, that may be a legitimate fear. I have not actually crunched the numbers here, but I suspect that when somebody fires a gun straight up into the air, that bullet will immediately slow down. It'll reach the apex of its trajectory. And at the top of the trajectory, should I do a little picture here? Okay. Here's the bullet. When it first starts out, we just saw that acceleration could be easily, I'll say it's greater than, here, the magnitude of the acceleration is definitely greater than g because air drag is slowing it down. Then when it gets to the top, for a moment, its velocity is 0. On the way back down, you've got drag pointing up and you've got gravity pulling down. And I probably should have drawn the drag force shorter, because this thing would still be speeding up. But remember, the faster it goes, the faster and faster and faster it goes, the greater the drag force gets. And at some point, the drag force really is equal to the weight. And at that point, the bullet's not going to go any faster. It's reached its terminal speed. That's the speed at which the acceleration terminates. And it shouldn't go any faster than that, because there's no outside force to force it beyond its terminal speed. Gravity is the only force in this instant. That's different from when it's fired from the gun, where you've got those expanding gases, after the gunpowder ignites. It's being forced out of the gun at a speed considerably greater than its terminal speed. I don't know what the terminal speed of a typical round is, and I certainly wouldn't want to test that and let it hit my head just to see what it is, but it's nowhere near as great as when it first comes out of the gun. But I'm not trying to discourage you from hiding in your closet with a cast iron pot over your head. I think that's enough on drag force for now. Later in the semester, when we've talked about work, the concept of work and kinetic energy, we will probably see some more problems that make use of drag. And also, like I mentioned, we may do a lab using Microsoft Excel where we predict the trajectory of a home run hit, a baseball home run hit, and we actually do incorporate the effect of air drag, in which case the trajectory is not simply a parabola. If you use regular old kinematics, and I just realized you're looking at nothing here while I talk, so I'll wrap this up. But if you use regular old kinematics to predict the trajectory of a home run hit, you get this enormous parabola. And for typical speeds of in excess of 100 miles an hour, let's say 110 miles an hour for the speed of the ball off the bat, you would find that this ball should go something like a mile, which is way beyond the actual baseball diamond, or the stadium, I should say the stadium. And you just don't see that. And that's because our regular kinematics have completely ignored air drag. The actual trajectory looks, well, on first analysis, it might look something like this. If you take into account the type of drag we've been talking about, I don't think it's supposed to bend backwards like this, actually, a little bit more like this. If you incorporate our quadratic model for drag into F equals ma, you can predict that the trajectory is much more like this, severely reduced. There is another type of interaction, though, between the air and the baseball, which is not treated in this chapter. It's called the Magnus effect, and I think I'll address that in another video. But because a baseball is often spinning, it's got top spin or back spin when it comes off the baseball bat, there's another interaction with the air that's different from this quadratic drag force. People call it the Magnus effect, and it corresponds to lift on the ball. So the ball might actually do something like this. It could go even higher than it would without air at all, without air drag. And it'll tend to go a little further than this first analysis. So I think we probably will do a lab where we rather easily incorporate those effects into F equals ma and trace out the trajectory of the ball.